Welcome. So you've probably seen headlines, a new study finds something is statistically significant. But have you ever stopped and wondered what that actually means? Well, in this explainer, we are going to crack the code on one of the most powerful and honestly one of the most misunderstood ideas in all of science, the p-value. All right, let's jump right in with a question that seems, well, kind of obvious, right? Of course they are. But how would you prove it? How would you know for sure that the taller players you measured weren't just a total fluke, just a random coincidence?
And that is the big question that statistics helps us answer. See, in any data we collect, there's always going to be some random noise, some pure luck involved. The real trick is figuring out if the pattern we're seeing is a genuine, real-deal effect, or if it's just the data playing tricks on us.
So, here's our game plan to get to the bottom of this. We're going to start by talking about the role of pure chance. Then, we'll look at the scientist's toolkit for dealing with it, called the hypothesis test. After that, we'll decode the famous p-value. And then, this is the best part, we'll hit you with the big twist about what significance really means. And finally, we'll wrap up with a guide to common mistakes.
Okay, first things first. We just have to accept that we live in a world that's full of randomness. I mean, think about it. If you measure just a few people to guess the height of everyone, you could, by pure luck, grab a group that's way taller or way shorter than average. Statistics gives us the power to see through that randomness.
So, how do we actually do that? How do we separate the real signal from all that random noise? Well, scientists have a system. It's a structured process, a powerful tool they use to put their ideas on trial. It's called a hypothesis test.
And it all starts by setting up two opposing ideas, kind of like in a courtroom. First, you have the null hypothesis. This is the default skeptical position. It assumes nothing is going on. It's the innocent until proven guilty idea. For our basketball players, it would be that they're the exact same height as everybody else. Then you have the alternative hypothesis. This is the exciting part. It's the claim you actually want to prove, that there is a real difference. Now, this whole process follows a clear set of steps, a kind of roadmap for our scientific trial. You state your two hypotheses, you decide how much evidence you're going to need to be convinced, you go out and collect the data, and then you run the numbers to see if your evidence is strong enough to reject that initial, skeptical, no difference idea.
And this brings us to the heart of the whole thing, the verdict. The one number that gets all the attention and causes all the confusion, the p-value. This is probably the most important and easily the most misunderstood number in statistics.
So what on earth is a p-value? The best way to think about it is as a surprise-o-meter. It answers a very specific question. If there's actually no difference, how surprising is the data I just collected? A really, really tiny p-value means your results are super surprising, which should make you think, maybe that no difference idea was wrong after all. Let's make this real. Let's go back to our basketball players. So imagine we do our study, we collect our data, and we find that our group of players is, on average, 9 centimeters taller than the average man. After we do the math, out pops this number, a p-value of 0.03. So, what does that actually tell us?
It means this: if, and this is a big F, if basketball players were actually the same height as everyone else, the chance of you just randomly picking a group that happened to be 9 centimeters taller would only be 3%. That's pretty unlikely, right? It's so unlikely, it makes you really doubt that initial no difference assumption.
So to make a final call, scientists draw a line in the sand before they even start. It's called the significance level, and usually it's set at 5% or 0.05. If your p-value is smaller than that line, like our 0.03 is, you get to declare your result statistically significant. And that means you have enough evidence to reject the null hypothesis and say, yep, it looks like there's a real effect here.
Okay, but hold on, because this is the part that trips almost everybody up. A small p-value is not the end of the story, not by a long shot. Stopping here is what leads to some of the absolute biggest mistakes in interpreting science, because statistically significant does not mean important.
This is seriously the most important question to ask, and the answer might surprise you. No, it doesn't. Statistical significance is a technical term. It has a very specific meaning. It has nothing to do with whether a result is practical, or important, or meaningful in the real world. And this example makes it crystal clear. Check this out. A drug trial finds a statistically significant link between a new drug and lower cholesterol. The p-value is tiny. Sounds amazing, right? But then you look closer. The actual reduction in cholesterol was so small it would make absolutely no difference to a patient's health.
The effect was real, sure, but it wasn't meaningful. It was clinically useless.
So here is the key takeaway. A p-value tells you about the existence of an effect. It tells you if there's a real signal in the noise. It does not tell you about the size of that effect. With a big enough study, even a tiny, completely trivial difference can become statistically significant. The p-value confirms the signal is there, but it doesn't tell you if that signal is even loud enough to care about.
All right, let's wrap this up by turning you into a critical thinker. Now that you know what a p-value is, let's look at how they're often misused so you can spot the problems from a mile away.
First, and this is a big one, burn this phrase into your brain. When a study finds a large p-value, a not significant result, it does not prove that there's no effect. It often just means the study was too small. It didn't have enough power to find an effect that might actually be there.
So here's your cheat sheet for the biggest p-value blunders. Never assume not significant means no effect. Never, ever confuse statistically significant with practically important. Always remember that with enough people, any tiny effect can look significant. And finally, the most common error of all, the p-value is not the probability that the no-effect idea is true. It's the probability of your data assuming that idea is true. It's a subtle difference, but it's everything.
And there you have it. Now you have the tools to look past the headlines and beyond the numbers. So the next time you hear that a finding is statistically significant, you can be the smart one in the room who pauses and asks the most important question of all. Okay, that's interesting, but is the effect actually big enough to matter? Thanks for tuning in.